Hello, so in this section I'm going to talk about adding and subtracting matrices. Now, when we talk about a matrix, one thing that you should realize is that it's kind of like it has dimensions. So for instance, we know that like the uh, the matrix, it's kind of like a structure. So we have that this right here would qualify as a row. So this is going to be a row, A, B, C. Or you could always say like row 1. This right here, the entries A and D represent a column. So we have column 1, column 2, column 3. Now, I circled this entry that I called F. So each of these values, they represent entries. So in this case, we have that, this could be row 1, column 1 entry. So an entry is just like a real number in either case. So the thing of which that we can say is that the dimension of this matrix is going to be, it's a 2 by 3. Why is that? Because it has 2 rows, 3 columns. Now, some things that we can look at is, for example, just a little bit of notation, for example. So let's say that you have a matrix, and we'll just write it like this. Let's say that you have a matrix that you have the entries A1, A2, A3, then you have A4, A5, A6, A7, and A8, and then A9. Now, this is a square matrix. So we have that this matrix right here is 3 by 3. But to be specific, we call these square matrices. Now, a square matrix basically has as many rows as many columns. So you should expect that, a square matrix is going to be exactly as it sounds. But we also have something called a row matrix. Now, whenever we talk about a row matrix, it's exactly as it sounds too. You have that there's just a single row of entries, so like A1, A2, and then A3, which in this case, the dimensions of this one would be 1 by 3. Another type of matrix that you might see is what we call a column matrix. So we have that there is a column matrix that we can have, and for example, we could use the entries B1, B2, and B3. Now, to be specific, we could say that the dimensions of this is a 3 by 1 because it has 3 rows and 1 column. Now, the other thing of which that we can mention is that we do have other types of unique matrices, for example. Like we have what is called the zero matrix. Now, a zero matrix is exactly as it sounds too, but you have to be careful. A zero matrix can have any number of dimensions. So like you have a 0, followed by another 0, followed by a 0, followed by a 0, and so on. So typically you may have to actually notate it as like a letter, or you might have to put like a little subscript that implies what dimensions this might be. So we'll just say, for example, that this is a M by N matrix, only because, it actually matters in terms of like what the dimensions of it might be. Another matrix that you might run into, for example, is what we call an identity matrix. An identity matrix is one of which where you have that it's defined as follows. You have I sub n. Now, a identity matrix is actually what we call a square matrix too. But here's how we define a identity matrix. An identity matrix could consist of 1, 0, 0, 1. And actually, let me just go ahead and make this more general. Okay, so yeah, it's a matrix of which consists of entries like 1 and 0. So 1, 0, followed by 0, 0, 1, followed by 0. And then we have that this would be a 0. And then we have that this would be also a 0, but then a 1. And then basically you have like a 1. And then that's it. Okay, so essentially this is just a matrix that has all 1s and 0s. So in this case, we would note that the dimensions would be n by n. Okay, now these matrices are actually very important as it relates to, let's say, like multiplication or even addition. So let's say that we go ahead and we start with the basics. So the basics are that, we want to be able to add and subtract. Actually, let's go ahead and let's go back. So actually, I need to look at the equality first. Okay, so you learn that basically that matrices have dimensions and they have entries. So one thing that we can say is that suppose that A is n by n, and then we'll just say that B is m by n. So if we say that A is equal to B, that means that not only do the dimensions have to be the same, we also have to have that the entries are the same, and that's specifically because of the equality. So this is the only way that these two matrices can be similar. So one way to demonstrate that is to say, like, for example, if you have 1, 2, 3, 4, and then you have that this is equal to x, y, z, and w, well, basically this tells you that x is equal to 1, y is equal to 2, z is equal to 3, and w is equal to 4. But it was only possible if the dimensions were the same, which in this case they are. So you have a 2 by 2 and you have a 2 by 2. So in this case you have that in terms of matrix equality, this actually does hold. However, what if you had that the matrix was different, where you had, let's say you had 1, 2, 3, and 4, but let's say that, for example, that you have that this is equal to 1, and then you have 3, and then we have a 2, and then we have a 4. Well, this is not true, specifically because of the fact that you have that there's some entries that are not in their right place. You have that there's one right here, you have that there's another right there, and then that's it, because yeah, you know that they don't correspond, basically, that these are not the same. So even though they are the same dimensions, you have that these cannot be the same matrix. Okay, well, what if we had something like a matrix like x, y, and z, and we said that this is equal to 1 and then 2. Well, this cannot be true either. Why? It's because the dimensions actually are not the same. You have that there's a 2 by 3, and then you have that there's a 2 by 1. These dimensions actually do not match at all. So in that case, you know that these two matrices cannot be they cannot be equal. Now, of course, basically this is just to talk about, like, the different types of equality. Now, of matrices. So you're going to need this like in the next section when it comes to matrix multiplication. But let's go ahead and just look at how we can add and subtract. So, um, okay, so we're coming back to addition because we kind of needed addition in order for this to work. So let's say that we look at addition and subtraction. Okay, now when it comes to addition and subtraction, the entries, they all must be the same. So, well, not the same, I'm sorry. The dimensions must be the same. So if we have that we have a matrix like A is n by n, and then we have that B is also n by n, then we can also introduce another matrix that is also n by n. So what that says is that basically you have that A plus B equals to B plus A. But notice that the dimensions are the same. If you have A plus B and then you add that to C, well, that's the same as if you take A plus B plus C. Okay, now we do have that the same thing works for subtraction, where we can say that, you know, that if we subtract, that it's more or less going to be the exact same thing. So that's one thing to look at. Now, so another way that you can actually look at the matrix addition and subtraction is that if you take an entry from your matrix A, so you have A sub ij, this is basically the notation where it tells you the row and it tells you the column. So what if I was to add this to the matrix B, but the entry was B sub I j? Well, in this case, this would have to equal to a new matrix, so C sub ij. So all that this is telling me that I can add component-wise, essentially. So if you want to put a minus sign, you can. And then the same thing goes for, like, if you want to put a minus sign for these two as well. But, you don't really have to. Okay, now let's go ahead and look at an example. So if we have an example of where we take a matrix 1, 3, 4, 5, and then we have that we're going to add this to 0, -1, and then let's say that we have 1, and then we have 2. Well, if we add these two, basically we just need to make sure that the dimensions are the same, which they are. So we have that this is going to be so we have that this is going to be 1, 5, 7, and then we have a 2. So this is the matrix that we end up with, which there's not really much to it, and it shouldn't be a surprise that this matrix is a 2 by 2. Now, another way of which that we can look at subtraction of matrices is as follows. So let's say that if we had that we wanted to subtract a matrix, so like let's say that you had 1, 3, 5, 4, 2, and then we had, let me see, 6, and let's say that we wanted to subtract, okay, so let's say that we want to subtract a matrix of which we have 9, 6, 0, 4, 3, -1, then we can actually solve this similarly. So first off, you need to make sure that the dimensions are the same. So this is a 2 by 3, and that's a 2 by 3. So the matrix addition or subtraction is possible. So we have that this is going to equal to, okay, so we have, okay, well 1 minus 9 is -8. 3 minus 0 is 3. 2 minus 3 is -1. And then you have 5 minus 6 is also -1. 4 minus 4 is 0. And then 6 plus 1 is 7. So we get that the matrix is as follows. Okay, so it's no surprise that, a 2 by 3 minus another 2 by 3 is still the same thing. Now, interestingly enough, like when it comes to matrix subtraction, you have that if I go ahead and I look at it like this, so let's say that we have a plus the negative of a, that's equal to a minus a. But if that's true, that's going to be the zero matrix, but it has dimensions m by n. Now, if that's also true, that means that if I take a and I add it, so if I take a and I add it to the zero matrix, that means that it's going to give me back the same thing. So that's actually pretty nice that we have a zero matrix and then it's in turn giving us an additive identity in this case. Now, the other thing of which that we can do is transpose a matrix. So whenever we talk about the transpose of a matrix, basically if you have a matrix A is m by n, then you have that a transpose matrix is basically n by m. Now what that means is that if you have a matrix like A, B, C, and D, and you're transposing it, basically that's equal to A, B, C, and then you have D. So not really much change with exception that these two are equal. So in this case, you have that these two entries would have to be, well, they don't really have to be equal technically. Yeah. But notice that it went from 2 by 2 to 2 by 2, so in a sense, like, that's where it gets a little weird when they're the same dimensions. But you kind of should get the point, is that, like if you have the following matrix, if you have like 1, 0, 3, 2, and then 4, and then 5, if you transpose this matrix, so notice that it's a 3 by 2, that you end up with the following. You end up with 1, 0, 3, 2, and then you have 4, and then a 5. So see like how the matrix has been transposed, and it has resulted in a 2 by 3. Okay, so the transpose matrix is actually going to be pretty useful for when we get to minimization problems using the simplex method. And it is used in further studies of systems of equations. Now, the last thing of which that we can look at is a simple problem where you want to solve the following matrix problem. So let's say that you have that there's a systems of equations. So you have x, and then you have 3, and you have y plus 2, and then you have z minus 1, you have w, and then you have a 5. Okay, now let's say that this was equal to the following matrix. So let's say that you have that this is going to be 6, 3, 1, and then let's say that this is going to be 8, 7, and then of course this should be 5. Okay, now notice that in terms of this we have that there's equality, so there's actually a lot being said there. You have that this is a 2 by 3 matrix and this is a 2 by 3 matrix, so that means that the entries must be equal. So if we do this problem, we can see that basically all that we need to do is just solve for the variables. So what that means is that x, well, that's equal to 6. Then you have that y has to be equal to -1. But then you also have that z, well, z is equal to 9. And then finally you have that w has to equal to 7. Now note that the only way that we could have proceeded on, or the reason why we proceeded on, was due to the fact that this 3 and this 3 over here, they're both the same, meaning that it implied that, that there is possible solution for x, y, z, and w. Otherwise, if there wasn't, then we would have stopped and said this is not possible to solve. So this is a typical question that's asked in an exam where you're trying to solve for the unknown variables if you have that the matrices are equal, but it's only if the dimensions were the same. Now, in the next section, you're going to look at matrix multiplication, and I'm actually going to have you come back to equality of matrices and solving those.